The future. In my beginning is my end. The quotation shows that how the universe, what is the beginning of the universe and what is the end of the universe. This is a mystery question. The answer of the question is not completely filled. The quotation is very clearly show how the universe. Will the universe continue to expand forever? The question answer of the question. This depends on how much matter the universe contains and on how fast it is expanding. There are three possibilities. Possibilities number one. If the average density rho of the universe is smaller than a certain critical density rho c, that is a function of the expansion rate. The universe is open and the expansion will never stop. Eventually, new galaxies and stars will cease to form, and existing ones will end up as black dwarfs, neutron stars, and black holes, and icy death. If rho is greater than rho c, the universe is closed, and sooner or later, gravity will stop the expansion. The universe will then begin to contract. The progression of events will be reverse of the that took place after the Big Bang, with an ultimate big crunch, a fiery death, and after the another big bang. If so, then the universe is cyclic, then the beginning and end. If rho is equal to rho c, the expansion will continue at an ever decreasing rate, but the universe will not contract. In this case, the universe is said to be flat because of the geometry of space in such a universe. If rho is equal to rho c, space is negatively curved. A two-dimensional analog is handled rho greater than rho c. Space is positively curved. A two-dimensional analog is the surface of the sphere. In all cases, however, space-time is curved. The graph shows how the space-time is curved based on the time. Okay. The graph shows the details of the graph, radius of the curve, time, Big Bang. Okay. To find the value of the critical density Rossi, we begin the same way we would not find the escape velocity from the Earth. The gravitational potential energy U of a spacecraft of mass m on the surface of the Earth, whose mass m is the radius r, the U is equal to minus g m by r. It is to escape the permanent from the Earth. The spacecraft must have a minimum kinetic energy of mv square such that its total energy is equal to 0. E is equal to k plus u half mv square minus g mm by r is equal to 0. This gives v is equal to root of 2 gm by r 11.2 for escape velocity. The escape velocity means that how what velocity we required to overcome the gravity of the Earth. For example, if a rocket shall be launched, the rocket must be travel in the speed of 11.2 kilometer per second. 11.2 kilometer per second. If the rocket velocity is greater than that, the rocket is successfully launched from the Earth. But the rocket velocity is reduced or less than that of 11.2 kilometer. The rocket does not launch. The rocket does not overcome the Earth gravity. So the launch is fall. Okay. Now we consider the spherical volume of the universe of radius r, whose center is the Earth. Only the mass inside this volume affect the motion of a galaxy on the surface of the sphere, provided the distribution of matter in the universe is uniform, which it seems to be on a large enough scale. If the density of matter inside the volume is rho, the volume contains a total mass m is equal to 4 by 3 pi r cube rho. According to Hubble's law, the output velocity to expansion of the universe is proportional to r. Hence, we use is Hubble's parameter. Hubble's parameter called the galaxy's mass m. If it has just enough speed never to return, we have half m square is equal to g m by r. C is equal to rho c is equal to 3h square by 8 pi g. The critical density for a flat universe depends only on Hubble's parameter h, which is not accurately known. A recent value for h is 21 kilometer per second. which is rho is equal to 8.9 into 10 raised to minus 27 kg per meter cube. The mass of a hydrogen atom is 1.67 into 10 raised to minus 27 kg. So the critical density is equal to somewhere near 5.3 hydrogen atom per cubic meter. Dark matter. The actual density, okay, dark matter is one of the non-reasonable questions around the science today. Dark matter, there is no completely solution to the question, or completely answer to the question. What is dark matter? What is dark matter? What is matter? What is matter? We know the what is matter. What is dark matter? The answer to this question is not completely clear by the science. The dark matter. The actual density of the luminous matter in the universe is just a few percentage of Rossy. Adding in the mass equivalent of the radiation in the universe increase the density only a little, but is luminous matter, the stars and the galaxies we see in the sky. The only matter in the universe apparently not very strong. Evidence indicate that the large amount of dark matter is also present. So much, in fact, that it is at least 90% of all matter in the universe is non-luminous. For instance, the rotation speeds of the outer stars is spiral galaxies are unexpectedly high, which suggests that a spherical halo of the invisible matter must surround each galaxy similarly. The motions of individual galaxies in clusters of them imply gravitational field about 10 times more powerful than the visible matter of the galaxies provides. Still, other observations support the idea of the preponderation of dark matter in the universe. What can the dark matter be? The most obvious candidate is ordinary matter in various established forms, ranking from plant-like slump to small to support the future fusion reaction that would make the stars through burn out dark stars. Two black holes. The snag here is that in the record numbers, such object would certainly have been detected already. Another possibility rooted that in what we already know is the sea of neutrons that pervades space. Neutrons appear to have mass, but very little, nowhere near enough to account for all the dark matter indeed. If neutrons were responsible for the dark matter, the universe could not have evolved to what it is today. Galaxies, for example, would have to be much. So neutron is to maybe part of the answer. There is no shortage of other possibility, all classed as called dark matter, which means that the particles involved are relatively slow moving, unlike neutrons, which constitute hot dark matter. Two main kinds of cold dark matter have been proposed: WIMPs and axions are hydrogen leftovers from the early moments of the universe. An example is the photonium, one of the particles predicted by the photon is supposed to stable and to have a mass of between the dark matter needed to account for the motion of the stars in galaxies is galactic clusters bring the total density of the universe up to about zero point 0.1 pc. There may be still more dark matter. However, in 1918, the American physicist Alan Guth proposed that the 10 to minus 35 seconds after the Big Bang, the universe underwent in an extremely rapid expansion triggered by the separation of the single unified interaction into the strong and electroweak interaction. During the expansion of the universe blew up the smaller than a proton to about a grapefruit in size. 10 to minus inflammatory Big Bang. Okay. One of the good conditions is if the inflammatory scenario is correct, then the universe is not only perfectly flat. But as the perhaps 90% of the matter is dark matter. Find nature is dark matter. Clearly, one of the most fundamental of our outstanding scientific problems, the dark matter. The graphs show that time since the Big Bang, radius of the universe. Big Bang.